here, let's take a look at this sample problem. It says in the figure it takes R to be this value and dB dt to be this value. So find the expression for the magnitude E of the induced E field at the point within the magnetic field at radius R. R is smaller than this capital R. So small r is 5.2 centimeter. Capital R is 8.5 centimeter. Okay, so of course we here will use the Faraday's law. So let us write it out. So this is the line integral of E dot ds, and then here we already suppose this is the Ampere's loop. The direction is counterclockwise. So actually E and ds points to the same direction on the whole path. So this is nothing but the closed integration of E ds. So the dot product, they are parallel to each other. The cosine 0 is 1. And then E is a constant. E is a constant because this is a circular region. And then this Ampere path also have the same center, which means this circle and the boundary are concentric circle. So yeah, so we assume that the E field are uniform over the whole path. So it is nothing but E closed integration of ds. So this one is nothing but the circumference of the circle, which is 2 pi r. So it is E times 2 pi r. Okay, so next on the right side we need to take the derivative of the magnetic flux. So let us write out what is the magnetic flux. Will be B times A. So already should be originally it should be surface integral, but actually here the magnetic flux are uniform and also changing with a static rate. So it is nothing but B times A, and actually the area sorry. The area here is nothing but pi r square. So B times pi r square. Okay, so let's take the derivative of the magnetic flux with respect to time. So pi r square will be a constant to time, so it is nothing but pi r square and then dB dt. So given by the question, it is 0.13, so it is 0.13 pi r square. Okay, so you can write out the Faraday's law as integration of E dot ds equals negative d phi b dt. Okay, so we can just plug in this one on the left side. So we have E times 2 pi r equals negative 0.13 pi r square. Then we can make some cancellation so that we can get E equals negative 0.13 over 2. Pi and pi can be cancelled. This r can be cancelled with this one. So we only have r here. So which is nothing but a negative 0.065 r. And then if we just consider the magnitude, which means that we take the absolute value. So E should be 0.065 out. And here we want to know the E field, the induced E field generated by this changing magnetic field at R equals to 5.2 centimeter. So actually we can just plug in E of 5.2 centimeter. So which is 0.065 times 0.052. So this is nothing but 3.4 millivolts per meter. Okay. So which is quite a small E field, quite small. And actually be careful that this M is not the same as this M. This is milli, this is meter, so they cannot be cancelled. Okay, for part B, it asks the same thing, but here it asks you the E field outside the magnetic field, which means the Ampere's loop should be outside. Yeah. Somehow like this. Okay. Yeah. So this is the Ampere's loop for this question, and it's somehow like this, and then yeah, actually we can just do it like d phi b dt will be d and then b times a and then over dt. So the A corresponds to the magnetic flux, so which means that this area is not the area enclosed by the Ampere's loop, but the yellow region, because we only have a B field inside the yellow region rather than here. Here we don't have any B field. So here the A should be pi capital R square rather than pi small r square. And then we have still have a dB dt. So this number is still the same, 0.13 pi capital R square. So here we have integration, closed line integration of E dot ds equals negative d phi b dt. Okay, so on the left side it is still the same, E times 2 pi r equals negative 0.13 pi capital R squared. So similarly we can cancel pi, but not the r, because on the left side is small r, on the right side it is capital R squared. So it should be E equals negative 0.065 and then capital R squared over small r. Okay, so if we take the magnitude, we should take the absolute value to the E field, so it should be 0.065 capital R squared over R. And here we need to evaluate it at R equals 12.5 centimeter. So this number is 0.065 and then capital R is 0.085 quantity square over small r is 0.125. So this is 3.8 millivolt per meter. Okay. Any questions? Okay, so here we talk about the inductors and inductance. So when some of you are ECE students, so they will learn. They actually are learning the circuit analysis. So for the fundamental circuit, there are three passive elements: the resistor, capacitor. We have learned it in chapter 26, 25. And here we learn about the last one, which is the inductor. So usually when we talk about the circuit theory, the three fundamental elements are R, L, and C: resistor, inductor, and capacitor. So here we talk about the L. So it says an inductor is a device that can be used to produce a known magnetic field in a specific region. So actually it is nothing but the solenoid we learned in the previous chapter. So in the previous chapter you already know this, the B field generated by the solenoid is B equals mu 0 IN, something like that, for a solenoid. Yeah. Okay, so usually it will be nothing but that, but yeah, there's some other structure. Okay, so if a current I is established through each of the N windings of an inductor, a magnetic flux phi B links those windings. The inductance L of the inductor is this expression. So phi B is the magnetic flux for a single turn. So it will be multiplied by the N, capital N, which is the number of turns of the inductor. So this is the total magnetic flux go through the inductor. This is normalized by the current. So you can regard somehow like if this one is normalized by I, so the value doesn't related to the current. And actually you can regard this, when you look at this equation, you can see the B field generated by the solenoid is proportional to the current. So if we just want to isolate the effect from the current, so we just define another variable, so that we just normalize it by the current, so that this L, this inductance, only related to the structure itself rather than the current. Okay, because phi B is proportional to the B field, because it should be like phi B equals B times A times, or probably times N, or maybe I just skip this one. Phi B is proportional to this, and A should be a constant, so yeah, it doesn't relate to the current. So B times A is proportional to the current, so we just define this value, then this value shouldn't be related to the current. Okay, and actually the SI unit for the inductance is Henry. Short form H, capital H. Okay, so if you don't really remember, I just recall it. For the resistance, the SI unit is ohm, and then for the capacitance, the SI unit is farad. For the inductance, the SI unit is Henry. Okay, so here it says the crude inductors with which microfarads discovered the law of induction. In those days, MNTs such as insulated wire were not commercially available. So yeah, so he cannot really bought the insulated wire. So he make it himself. It is said that Faraday insulate his wire by wrapping them with strip cut out from one of his wife's petticoats. So yeah, so the petticoat sacrifice for the development of the physics. So like this one. So the Royal Institute Art Library. Yeah. So this is the one created by Faraday. Okay, so next, yeah, suppose we have this one, because for this equation we have n phi b in the denominator. So let's take it out. N phi b is actually, n is the number of turn per unit length, and L is the length of the inductor. So n is small n times small l, and then for phi b it is nothing but b times a, so nothing special here. So where n is the number of turn per unit length, and then yeah, just mention b is mu 0 in, so we can plug this one here, so that's all together, and then we plug this one in the previous formula. So we have L n phi b over I, and then n phi b is this one. So we have n small l and then ba over I, and then we can plug this one into here, so that we have nl mu 0 in capital A over I, and then we can just cancel this I with this I, and then we move this L to the left side. So this is the inductance per unit length equals mu 0, and then n square, and then A, and then nothing else. So this is the inductance per unit length equals this value. So this value is, the first one is a constant, the permeability constant. So nothing special, it's just a constant. And this is the small n is the number of turn per unit length. So if you want to make this one larger, then you should either make this n to be larger, to have more turn in a unit length, or you can make the cross-section area to be larger. Like for this one, it is smaller than this one. You should make the inductor with a larger cross-section area. Okay, so this is okay. So here it talk about the self-induction. Yeah. Okay, so here it says if two coils, which we can now call inductors, are near each other, a current I in one coil produce magnetic flux phi b through the second coil. So here, the first coil and second coil means, suppose this one is the, maybe I can highlight it with a color. So it means that if you regard this one is the first coil, and then the second coil is this one. If they are close to each other, and let's see what is this circuit. So here is a battery, this is a resistance, and then here is an arrow, which means that this arrow can be sliding over the resistor, make it a tunable resistor. So this is a tunable resistor. So if this tip point is here, then the current should go through the whole resistor, then the resistance is larger. If this tip point moves to somewhere here, then the current only goes through a shorter path. Most of the part of the resistor, the current didn't go through, so the resistance will be smaller. Actually, in the lab section, you will have a tunable resistor like this long, and then you need to do many sliding stuff there. Okay, so this is a tunable resistor, which means that you can control the current going through here, because this is E, this is a DC battery, and then you can consider the whole resistance over this path. Then you can determine the current by the Ohm's law. So E over R will be this current. So you can control the current here, and then you can simply imagine, suppose you have the current going through, for example, the red coil. Then for this coil, if it has some current going through it, then this coil will generate a B field. The direction is like this. The direction of the current is like this. So the B field is pointing which side? Upward or downward? The B field should be pointing downward. The B field generated by the red coil, because using the right hand rule, your forefinger follows the direction of current, and then your thumb pointing to the downward. Okay, so according to the Faraday's law, as much as you have some B field is increasing, pointing to the downward, then according to Faraday's law, this one will generate the induced EMF, which is pointing to the opposite side, because the B field is pointing downward and increasing. So the induced B field is pointing upwards to cancel some of the B field, and of course there will be some EMF. So which looks like this inductor will have a voltage drop across it, or the EMF is the other way around, or somehow like the induced EMF. Okay, so here it says we have seen that if we change this flux by changing the current, if we are increasing the current, an induced EMF appears in the second coil according to the Faraday's law, and an induced EMF appears in the first coil as well. So this process is called self-induction, which means that one of the coils has current, then it will generate the magnetic flux over other coils, and then the coils governing by the Faraday's law, it will generate some induced EMF in the opposite direction. So and the EMF that appears is called the self-induced EMF. So it obeys the Faraday's law of induction just as other induced EMF do. Okay, so here it says, thus in any inductor such as a coil, solenoid, or a toroid, a self-induced EMF appears whenever the current changes with time. If it is just a DC, then the EMF will disappear after a short moment. Depends on the L over R values. Okay, so the magnitude of the current has no influence on the magnitude of the induced EMF, only the rate of change of the current counts. Okay, so here it says still the same thing, N n phi b equals Li, because for the definition, L equals n phi b over I, so we just move the I to the right side. And then for the Faraday's law of induction, we have E equals negative n d phi b dt, which means that we just or put this n inside. So we take the derivative on the right on both sides. So we have d n phi b dt, and then we have a dt L times I, like this. So this one is actually this one with a negative sign on the. So we have this one, and then this one is actually dli dt. So here it becomes dli dt, and L is a constant, so we just move it out. So it becomes negative L di dt, and on the left side is the induced EMF. Actually, this is the this is how it is written on the textbook in a physics point of view. For circuit point of view, I usually write it as V equals L di dt without the negative sign. So for circuit theory, it's just like in circuit analysis, I seldomly use the EMF, the concept of EMF. We usually regard it as a voltage, as a potential difference. Like, so this is a battery. So the VL, or maybe I can write it as a VL, means the voltage drop or the potential difference across the inductor. So it is defined like this. So for the inductor, the VL, this side will have a higher voltage, this side will have a lower voltage, or you can just regard it as a battery with a reverse sign. So it is actually the same, just depends on how you look at it. If you regard it as a voltage drop, this is positive, this is negative. If you regard it as a EMF, you can regard it as a battery or as a EMF. So this EMF is a negative induced EMF. So this one is a negative value, or EL, with a negative sign. So they're actually the same. But usually I just regard it as a voltage drop. I usually use this one. And actually in chapter 27 and chapter 31, I mainly use this one rather than the EMF. Okay, because we need to use it to write something like the differential equation, constant coefficient ODE, and then we need to. I will teach you how to solve the constant coefficient ODE, which will be helpful to you not only for circuit, but will be helpful to other engineering problem. Okay, so yeah, so this is how I usually use, and I'll use it later. Okay, so here an induced EMF EL appears in any coil in which the current is changing. So here the important point is current is changing, because this is the derivative of I with respect to time. If the I is not changing, which means I is a constant, then this term is zero, then the EMF will also be zero. But if I is changing, then this term is not zero, so the EMF is not zero. And it depends on whether the I is increasing or decreasing. If I is increasing, the right side is a negative number. If I is decreasing, then this one is a negative, is a positive number. Okay, so actually this part related to the differential equation. Yeah, actually I have not teach you how to solve it yet, but I try to let you know a bit. Okay, so actually we need to use the KVL, the Kirchhoff current law, the Kirchhoff voltage law, KVL, the Kirchhoff voltage law, to write equation describing this circuit. So here, usually we can just define any point to be a ground, which means the voltage is 0 at the point, and then starting from here, this is a battery, so this is 0, this is E, this is E, so this point is E volt, and then you can also expect that this is a battery, this is positive, this is negative, the current is going clockwise, in the clockwise direction. Okay, so in this case, there will be a voltage drop. There will be voltage drop for this resistor. The voltage drop is I times R, according to the Ohm's law. So this voltage, VR, is nothing but I times R, like this, I times R. So from 0 going up and then going down and then go down again. So this VL is L di dt, L di dt. This is positive, this is negative. So we can write out the KVL as E equals I times R plus L times di dt. Okay, so this is an equation, but with a differential here. And of course, we would like to solve this so-called constant coefficient ODE, the constant coefficient ODE. I will try to systematically talk about how to solve first or second order constant coefficient ODE later, after this chapter. But yeah, but the point here is that this is actually the answer to this one. This is actually the answer to this one. Okay. Okay, this will be the solution to this differential equation. Okay, yeah. Okay, so I do not try to tell you how to solve it, but if you don't believe, you can at least try to plug in this one into here. So I is this one, plugging into here, and then you need to take the derivative of this expression with respect to time, so this constant becomes 0. And then for this exponential, this is negative 1 over pi tau L, and then you can just multiply out according to the chain rule. Then you can find that this is actually the solution to this equation. So far just try to understand it like this. And yeah, so if you can accept this is the answer to this equation, and then let's take a look at what it is. So this is an exponential function, and we usually start from t equals 0. We start from t equals 0. So if we plug in t equals 0 here, e to the 0 power is 1. So 1 minus 1 is nothing but 0. So at the very beginning, it is 0. So here VR is nothing but I times R. So it just multiplied by a constant. So without this R, so it becomes E times 1 over. So we can write it as, so it is E times 1 minus e to the negative t over tau L, like this. So at the beginning, at t equals 0, this one is 0, like this. And actually, if we consider t to be infinity, this exponential to negative infinity will be 0. This one will be 0. And it becomes 1 minus 0, which is 1 times e. So this is e. This is e. And then it is an exponential. This is an exponential decay or exponentially settling. Okay. And here, this tau L is called the time constant. it determines how fast it will go from the initial state to the steady state. So we usually call this the steady state. Steady state. In Chinese called 稳态. Steady state. And then this is called the initial state. 起始态. So this tau L determines how fast it will go from the initial state to the steady state. And this tau L is the ratio between the inductance and the resistance of the circuit. If this number is faster, then it will go like this. If this number is larger tau L. If it is smaller, it will be something like this. For smaller tau L, like this. Because you can simply imagine, if T is tau L, then T over tau L is 1, so it is e to the negative 1. E to the negative 1 is 0.3 something, 0.368, if I remember correctly. So e to the negative 1 is approximately 0.368. And then you can just plug in it here, so it becomes 1 minus 0.368, which is around 0.632, which is somewhere around here. Okay, so this tau L, which is called the time constant, and in engineering sense, usually if T is larger than 5 tau L, then we can regard it arrives the steady state, because it can never goes to the steady state, as this one will be larger than, this term is always larger than 0 until T is infinity, but you cannot go to T is infinity. So this one is always larger than 0, which means that this term is always slightly less than 1. Always less than 1. But if T is large enough, say 5 times the time constant, then we can regard it is already the steady state. Okay, so like this, and yeah. And the next thing is, if we try to switch off this battery from the steady state, then the current will go from E to 0, which means that we only have this term rather than the previous term. Actually, I will try to tell you how to derive it later. So let me finish this sample problem first. Okay, so here it says the figure A shows a circuit that contains 3 identical resistors. This is 1, 2, 3 resistors with resistance capital R. 2 identical inductors. This is 1, this is 2, and then an ideal battery with EMF E to be 18 volt. This is 18 volt. What is the current I through the battery just after the switch is closed? So before the switch is closed, there should be no current, because no any current can go in. I equals 0 when T is smaller than 0, before the switch is closed. So there is no current can going out, and in that case there will be no current. But just slightly after the switch is closed, which means that just after just after the switch is closed, which means that it is the initial state. Initial state, it starts to changing. It starts to changing. So just after the switch is closed, and one thing we need to remember is that the current of the inductor is continuous. The continuous. This is not true for the voltage of the inductor or the voltage drop for the inductor. This it does not necessarily continuous. And for the voltage difference of the capacitor. Voltage factor of the capacitor is continuous. Okay. So these are the difference between the inductor and the capacitor. So we might need to slightly remember this fact. The current of the inductor is continuous, and I just mentioned just before the switch is closed there is no current. So just after the switch is closed there is still no current going through this inductor. I is 0 for this one. I is 0 for this one. So the only current can go through this resistor only. Okay, which means that this path is open, this path is also open. Okay, so in this case, I going through the battery is nothing but this path. So this path using the Ohm's law, this is the voltage difference for this resistor. So this is 18 over 9 ohm, which is 2A. Any questions? Okay, so for the next one, what is the current going through the battery long after the switch has been closed, which means that you can regard it as t tends to infinity. When t tends to infinity, just mention that when t tends to infinity, then the VL will be 0. VL will be 0. It becomes a short circuit because when t tends to infinity, the current is 0. The current is tends to 0 or very small value, or at least the slope of the current is very small or tends to 0. Because dIdt will be 0. So we have VL to be 0. So in this case, you can regard the L to be short circuit. You can just ignore it. So here, the point is the inductor, the voltage drop of an inductor at steady state, which means that dIdt is 0. Is zero. So there will be no voltage drop, so you can just regard it as a short circuit. And in this case, we can see that these are 3 resistors in parallel. So R equivalent is nothing but R over 3, which is 9 over 3 equals 3 ohm. Okay, so in this case, the current going through the battery. So here you can see it as this is E, this is R equivalent, and then like this. So here the current I is E over R equivalent, which is 18 over 3, which is 6A. So these are the difference. For the initial state, this path is open, this path is open. And then the current is 2A. And then at the end, for the steady state, the inductor can be regarded as a short circuit. So there are 3 resistors in parallel. So the resistance for the equivalent resistance is smaller, so that it leads to a larger current. Okay, so let's have a 10 minutes break.